All right, so here we are. We are in section 9.3. The title of section 9.3 is a normal distribution. So what we're going to continue talking about this idea of probabilities and means and distributions and all of that, and we're going to try to kind of tie some of those loose ends together. So in the first two sections of this, up here in section 9.1, we talked about different ways to describe data sets using means and standard deviations. And now we're going to kind of bring that back around and talk about probability and how probability is related to those. So in this session, we're going to take a look at continuous random variables. We're going to talk about continuous probability models, the standard normal curve, and then just plain old normal curves, and then calculating probabilities for continuous random variable experiments. All right, so probability. We're going to talk about continuous random variable scenarios. And so if you think back to the probability that we calculated back in 7 and 8, the probabilities we calculated for those probability experiments had a random variable that was discrete. And so the random variable could have been 2, it could have been 3, but it wasn't allowed to be anything between 2 and 3. It could be 2.5. Okay? We were rolling dice, but there was no way to roll the dice and get a 3.7. You got a 3, you got a 4, but you didn't get a 3.7. So we had discrete random variables. Discrete random variables gave us probability distributions that were discrete. So we had things like this, but this had to be a number up here, like it was a 2 or a 4 or a 6, but there was no such thing as a 6.2. It couldn't be that. And then, of course, we had associated probabilities. Whatever those probabilities were, it really didn't matter for this discussion, but we had discrete random variables. In this chapter and in chapter 18, we're going to explore the idea. So here, for the rest of this chapter and in chapter 18, we're going to talk about continuous random variables. And so a continuous random variable is a random variable where the value of x, that random variable, can take on any value in a range. So someone's going to give you a range of values and say it has to be in this range. Okay? So a continuous probability distribution is a continuous probability, is a probability distribution for that continuous random variable. Okay, here's where things get tricky. Last chapter, this was a probability distribution. It had all the random variable values x, and it had all of the probabilities p of x is down there in that second row. But that only worked because I had a discrete random variable where I could figure out what all the x's were. And if I could figure out what all the x's were, then I could find all their probabilities and I'd be good. When I have a continuous random variable, now suddenly this gets a lot harder. And my challenge is how do I figure out all of the probabilities if my variable value can be infinitely many things? What I mean by that is, if I told you that I had a probability model where x had to be between 0 and 4, how would I find all those probabilities for x? Because there's infinitely many numbers in there. So I can't make a table like I did before because my table will what? How would my table have infinitely many values in it? So what I'm going to do, what the argument is that we're going to make here, is that our continuous probability distribution for a continuous random variable is going to be a function. And so we're not going to treat it like this. We're going to say that our continuous random variable is going to be some sort of a function now. And then that function can be graphed and it can take on all of the values. Now, the most common one that you're going to see in this chapter, and then we'll see it again in your stats class, is called the normal distribution. The normal distribution is a continuous probability distribution, meaning it is a function for some random variable x. Okay? It is arguably the most important continuous probability distribution in all of statistics. And then the graph of it, when you graph that function, is called the normal curve. And this is it right here. Okay. So that picture right there, That's our continuous probability distribution. Now, if you think back to your algebra class, okay, your horizontal axis here is your x, so that's going to be your random variable. It looks like I've got two asymptotes on both ends of this where that graph comes down and approaches that horizontal axis out there. And then I got this symmetry going on here in the middle where it looks like the left side and the right side are perfect reflections of each other. Okay? The properties of that normal distribution that we need to be comfortable with are the mean, the median, and the mode are all the same value. They're this thing right here in the middle. So that middle value where that peak is, that's both the mean and the median, and as well as the mode. Okay? The normal curve is bell-shaped and symmetric about the mean. Okay? So left side, right side, perfectly symmetric. Here's where probability comes in. The total area under the curve is equal to 1. So if you think back, remember way back when, back in 212, when you were doing calculus and you had problems like this, someone said, here's some function f of x, and then here was an a, and here was a b, and your job was to find that area right there. And you say, oh, that's just an integral from a to b of f of x dx. And you did some math and somehow the answer came out to be 9 or something like that, where that area there was then 9 square units, whatever that meant. Same thing here, except for now we're saying that all of this area under this curve just simply adds up to 1. And that is true because if this is a probability distribution, then the sum of all the probabilities for a random variable must add up to 1. Right? This next little bit here says that on that normal curve, you've got those asymptotes. It never touches the x-axis as it extends further and further, but it approaches. So out here, you're going to get an asymptote. Out here, you're going to get an asymptote. Right? You'll notice that the shape of the graph changes. So I'm going to erase some stuff here so I can talk about the shape. I'm going to ask you to go back to calculus, to 212, and I'm going to ask you to remember stuff about this guy. Do you remember the second derivative? And when you would use the second derivative to determine where the graph was concave up versus concave down? When you look at this normal curve, you see here in the middle, there's going to be a chunk where the graph is concave upward, or I'm sorry, downwards. And then out here on the ends, it's going to be concave upwards. Right? And that spot where it changes from concave down to concave up, or concave up to concave down, remember those had fancy names, those were called inflection points. Right? Those inflection points are going to occur exactly 1 standard deviation below and 1 standard deviation above the mean, right? Remember the sigma right here, I'm sorry, that mu right there is our mean, and that sigma right there is our standard deviation. So between 1 standard deviation below and 1 standard deviation above the mean, those are the places where that inflection happens, that change of concavity for those inflection points, right? A couple other reasons why we really like this normal curve, besides all the obvious stuff about how beautiful it is this piece right here, the 68, 95, 99, 7 rule, also sometimes called the empirical rule. Okay? The empirical rule just simply says that 68.3, or roughly 68% of your population data lies within 1 standard deviation of the mean. 95 lies within 2 standard deviations of the mean, and 99.7 lies within 3 standard deviations of the mean. Now, I know what you're thinking. That's really cool, but what does it mean? All right, so you've graduated from Glendale Community College and you have landed your dream job. You now work at the Coca-Cola bottling plant and you work in quality control. So your job is to make sure cans of soda have 12 ounces in them. So you want the average amount of soda, the average to be 12 ounces. And let's say that there's a population standard deviation of about 0.01 ounces. Okay? That means that from here to here, now if this number is 12 and my standard deviation is 0.01, that number right there would be 11.99. And that number right there would be 12.01. That would mean that in there, that region represents 68.3%. Or if I went down to the assembly line and grabbed a can of soda, I'd have a 68.3% chance that can of soda would have somewhere between 11.99 and 12.01 ounces in it. If we go out 2 standard deviations, and let me change color here. So this would be, let's see, 12.02, and that would be 11.98. Then in between those two values is going to be 95% of our area, 95.4. So then if I went down to the assembly line and grabbed a can of soda off the assembly line, there'd be a 95.4% chance that can of soda would have between 11.98 and 12.02 ounces in it. And if I go bigger, if I go all the way out to 3 standard deviations below and 3 standard deviations above, which would be 12.03 and 11.97, then I'm going to have a 99.7% chance that if I walk down there and grab a can of soda, it'll have between 11.97 and 12.03 ounces of soda in it. Now, realistically, that's everybody. I know it's not. But realistically, 99.7%, that's close enough to go 100 to say that's everybody. That's one of the other reasons why we love that curve. The normal distribution. Okay? In general, any continuous random variable can be modeled with a probability density function. So if there's a way to measure it, we can find a curve and an algebra that'll work. Okay? There are only 2 requirements. 1, the total area under the curve must be equal to 1 for the interval that we care about for the function. And 2, well, the function can never go negative. Meaning the function will always be above the x-axis, because if it went below, then the area under would be negative. Remember that from calc? And then if it was negative area, negative probability, and negative probability doesn't make sense. So it can never go negative, right? Now, when we start changing the mean and changing the standard deviation of a data set, it's going to change how that graph looks, okay? But in general, a normal distribution can have any mean and can have any positive standard deviation. So by definition, standard deviations have to be positive. Okay? So we won't have any negative standard deviations. It just can't happen. Okay? The mean gives us that location of that line of symmetry, or the reflection, and the standard deviation describes the spread of the data, how spread out it is. Here I have 3 graphs. If you take a look at the first 2 graphs, these 2, on the left over here, this one and this one, they both have the same mean. They both have a mean. These are populations that have a mean of 3.5, but the one on the left has a larger standard deviation. The one on the right, or in the middle here, but the one on the right of these 2, has a smaller standard deviation. A larger standard deviation means that those inflection points have been pulled out. They've been stretched out left and right, so that's been moved away from the middle. And when you move those away from the middle, the top has to go down. Right? The one on the right here, this one, has a smaller standard deviation. So those standard deviations, those move those inflection points to the middle, and when you squeeze the sides in, the top has to go up. Now the reason that the top has to go up or the top has to go down is one of the rules says that this area has to stay fixed at 1. And if that area stays fixed at 1, then stretching it out means the top has to come down, otherwise there'd be too much area. Or pushing it in means the top has to go up to make sure that area stays at 1. Now, if you compare these 2 graphs, they have different means, but they have the same standard deviation. So their shape is the same, but by changing that mean, all I've done is I've taken the entire graph and moved the entire graph to the left by going from a middle at 3.5 to a middle at 1.5, but the spread is the same. The standard deviation is the same. All right, let's take a look at an example. Here I have the scaled test scores for the New York State Grade 4 Common Core Mathematics test, and I am told that these scores are normally distributed. All right, get comfortable with that phrase. When the grades are normally distributed, that means that we have a continuous random variable and that it is a normal curve that models it. Okay? So that means it's going to take this shape down here. It's going to look like this in some way, shape, or form. Okay, when I look at this graph, I'm asked to find the mean and estimate the standard deviation. Well, since this is a normal distribution, my mean is going to be where the middle of this thing is. So it looks like the middle's about there. So what is that? It looks like it's somewhere between 280 and 330. And so what's the scale? Looks like we're counting by tens here. So that would be 290. That would be 300. That would be 310. So maybe 305. So it looks like my mean is about 305-ish. Okay. I can't be exact because, well, I don't have an exact enough tool to measure this. Right? All right, how about the standard deviation? Well, the standard deviation is right there where those inflection points are, right? So I'm going to take a look and see if I can kind of eyeball where that inflection point is. It looks like maybe about there and there would be where our inflection points are. So that looks like it's about, I don't know, 240, 56 to about 260 right there. And so if the middle's 305 and that's 260, that will be a standard deviation of about 45 or so. So a normal distribution. I'm going to stop the video here and we'll come back and start part 2 right here using the normal curve to calculate probability. So I'll see y'all back here for part 2.